Good morning, everyone. We're back for
Mm.
part two of our math methods rehash for you all. This morning, joining me, we have Miss Helton and Mr. Nolan from KECSAC. And do you all want to introduce yourselves? Dwayne, you want to start us off?
I'm Dwayne Williams. I'm the math consultant for the Greater Louisville Education Cooperative, servicing Jefferson County Public Schools.
I'm Kelly Thompson with KEDC. I have the northeastern portion of Kentucky, and I'm a math consultant.
And I'm Stephanie Kidd. I'm with Kentucky Valley Educational Cooperative. I'm east and south. And so I'm right below Kelly. And so I work with, alongside each of our other state cooperatives.
There are 9 state surtax, as we're called in the state. We have a list of our names and a contact information for you and a map so you can figure out to which region you belong if you're not sure. Coming up in the slides in just a second. I'm Cricket McClure. I'm at OVEC, which is the regions around and other than special ed, including Jefferson County. So Ohio Valley Educational Co-op, sorry. And I'll pull the map up for you and let's see if we can. Oh, it doesn't want to share.
It's sharing Cricket. It just doesn't want to forward.
Oh, here I am again, guys. Where's my... Well, I need to get into it though to be able to see it. Okay, here we go. And that's not the first slide. Wait a minute. Oh, this is all the way at the bottom. Wait a minute. Okay. Now we're ready. I'm so sorry. Here we go. Here's the map of which we spoke. If you're not sure which, and you have this, you have access to this, so you don't have to squint right now and look. But you can see which region you're in. They're color coded. Once you know the region, then we have our names and contact email addresses by region. So once you know the region, find us. We are free to you. You are part of our mission in life, and we would be happy for you to contact us for anything to do with math, any way we can help at all. I'll put that again at the end also, I think. So, and then your directory, and then Dwayne put together this collaborative so you can figure out, again, a couple different ways to go at it, folks, but you should be able to find us. If you have any difficulty, contact one of us and we can put you in touch with the rest of us. We wanted to start last week, or 2 weeks ago, we started off with some other things and got into a little bit CSA. We did a little bit with algebraic thinking and some patterning to lead kids to the algebraic thinking. And today we promised we would do some beginning work with integers and some more algebra leading into algebra tiles as a wonderful manipulative for you to use with your kids. So in working with integers, I just finally saw an elevator. This is not my slide, I mean my picture, but I finally saw another elevator that actually has negative numbers for the floors that are below ground level, which I thought, duh, and kids would be much more familiar if they saw these things. We were hoping to give you some ideas here for real life applications of negative numbers, of integers, because kids encounter them all the time. And people who teach elementary school, if they say you can't take a bigger number from a smaller number, they're pretty much inadvertently lying to kids because you can, and kids know that. So negative numbers are real. They're in the world. They're part of life. We need to start looking at them in that context, putting them in context for kids. So here are a couple of others. Right now with the Derby Festival and everything, I watched balloons Saturday night, going overhead as I was driving through. So hot air balloons rise and they descend. So there's another possible real world example. Another one is temperature. Kids all know we go below zero. They hear it every year. So how much, how little, and that literally you're looking at a vertical number line, aren't you? So you can use that for integers also. Then Dwayne, you want to talk about football?
And then we can take a look at the football field. and talk about positive yardage that a team gets when they're moving the ball. They could get tackled for a loss, or the quarterback gets sacked, which is a negative number. And then they can get a negative number coming up if they get a penalty called on the offense. But if the defense is called for a penalty, the offense would get a positive yardage gain. So it's another way, and you could use the field as a mini number line, starting them out like the 20-yard line, having a run to the 30, then they get penalized 5 yards, and have them marking that with either a colored pencil, two-color counter, something like that, just so that they can keep track of where they're going with their positives and their negatives. And another example that you could use, and they don't even have to know how to play golf, but in golf, you're looking at who has the lowest score at the end. So one of the questions you might ask was who had the lowest score in round 1 of the golf tournament, and then have them figure up all of the scores for the 4 players, where they're at after 3 rounds of golf. Like Mr. Wallace in this example, -5 plus -1 plus -2 is -8. And then Rob has a +1, -3, which equals -2. And then a -1 takes him back to a -3. And then for Mr. Miller, that first round, he was terrible. He had a +10 plus 2 is 12 minus 3 is a -9. And then far is a -3 plus a -4 is a -7 plus 5 equals a -2. And you could end up asking them as a last follow-up question, who had the lowest score over those 3 rounds? And that would be Mr. Wallace. And one thing that the students have to look at is how the questioning is asked, and making sure that they're not adding everybody's scores up and they're doing each individual person's. But it's a great way to teach integers.
And football being right up your alley too, right?
Absolutely.
I don't know if these are any longer available, but I had for years some black on one side, red on the other side, integer square pieces. You could make these out of cardboard or construction paper or whatever. I'm looking for someone to do them again because they were a wonderful way. I personally prefer the squares. I know a lot of people have the circles that are yellow on one side and red on the other, and they work fine. But the squares lend themselves to the array model, which we're going to explore in a little bit with the algebra tiles. So just a thought. And then Stephanie.
So I love a bead string, always have, always will. And the bead string allows us to really see very much like a number line. And that's the reason I put the number line below it. So when we do this, Cricket, can you give me the option to share my screen?
I did, I think, yeah.
Okay. I want to see what I can do.
Look, now I have to stop sharing, sorry. Go ahead.
Okay. Let's see if I can do just pin. Did it? If I can pin just my picture, can we, you think that would work? To where everybody can see it very well? Does that work? Can everybody see? Okay, thank you. Now, so what I do is I tell them to think of red as negative, and we always use red beads for the negative. I've had white beads for positive. We've had black beads for positive, whatever you may want. And you can use even just the poly beads and just create these. This has 20 on one side and 20 on the other so that we can have larger numbers. And I also always show my students a pattern of some sort. And so they start to see a pattern that they're going to be developing. So a good example is if I did 3 plus 2. we would start out with all of the beads pulled away and having nothing in the center. And so you can see that. And then I would say, okay, let's bring over 3 positive beads. This is something they already know. And then I would say, okay, now can I add 2 more positive beads? Yes, I do. And what does that look like? And so at this point, they would say 5. And so we would have 5. And then I would say, well, what happens if I have -3 and +2? And at this point, we've done a lot with 0 pairs. So they have seen, and that's the reason why I want to go kind of back, that they can see that these are kind of like a battery of a positive and negative, and they repel each other. And so to have 0 pairs, I would have to have 2 negatives and 2 positives. And we would do this several times. What would be a 0 pair? Show me 0 pairs of, good example, 4. And so they would show me 4 negatives, 4 positives. We would do this several times. And then I would say, okay, now that we've got -3, can you show me -3? They will pull over -3. We'll pull over +2. And I would say, do I have any 0 pairs there? And they would say, yes. And so I would say, remove the 0 pairs. And so they pull them off together. And so as we pull them off together, what is my answer? And in this case, it's a negative because there's 1 negative there. And I have -1. Now we're going to do this again because now we're going to do 3 plus -2. And what does that equal? And they're going to see it again. And so I say, okay, bring on 3. And we're going to add -2. I can do that. They're going to see this. And we can do the jumps on here too as we're doing this if we need to. So if I've got 3 and I'm here and I'm saying, okay, I'm going to add -2. I'm going to actually jump which way because of the 0 pairs. And where am I going to land? And so if we do 0 pairs, I pull them off. And where am I at? I am at +1. Now, the next one that they do is -3 plus -2. And again, pull on 3. I'm adding -2. Where am I at? -5. And then we talk about the pattern that they see. And so we've done this several different ways. We will do it this way. We will do it on the number line so they can see it on the number line. We will talk about the pattern that they start to see. And in this case, they notice what? What do you notice? I have good wait time. Nobody wants to speak about what you notice about this?
You all can unmute, it's fine.
Cricket, do you want to say something you noticed then?
I noticed -5.
Ooh, yeah. Interesting, isn't it?
So I noticed you began with all positive numbers,
Mm-hmm.
and then you moved to adding negative and positive numbers. And then you added 2 negative numbers.
What did you notice, Kelly, about the 2 that I had a negative and a positive number that you didn't think about at first?
Well, the largest number was negative on the first one, and we ended up with a sum that was negative.
Oh, good. Yes. And on the second one,
the smaller number was negative, and we ended up with the sum being positive.
yes. And then when I had 2 negatives, we ended up with a negative answer, correct?
Mhm.
So let's do this with subtraction because that's where it gets interesting, and we usually have some problems with it. So we've had all these discussions. Go ahead.
Can I say something here? When Cricket was talking about the black and red tiles, it works the same way. You would lay the tiles out, and then you put the red ones over top, and whichever tile is left, then that gives you the answer. The red being negative or the black being positive. So if you don't have bead strings and you have those 2 colored tiles, you lay those out according to, what your calculations would be, and then those are left over. So those work really nicely too, but I love the bead strings, and I love to hear Stephanie do the bead strings.
So now we have 3, positive 3. And I'm asking to subtract 2. So I'm just going to take a positive 2 away. Can I do that? Do I have a positive 2 to remove? I do. So I remove the positive 2, and what am I at?
Positive 1.
Good. Now let's do a negative 3, and I need to subtract a positive 2. So I've got a negative 3, and I'm going to subtract a positive 2. Do I have a positive 2 to remove? No. I see a head shaking of no. So now I create 0 pairs because I'm, excuse me, I'm technically only adding a 0 to it if I create 0 pairs, but I need to create a 0 pair to where I get a positive 2. So bringing over a 0 pair, and I love it because my kids can pick these up and push them together. There's 1. Now I need a 2. So let's do 2. And your kids will actually pull over 2 at a time. But now, can I take a positive 2 away? I've got a positive 2. I'm going to remove it. And what am I left with?
Negative 5.
Negative 5. Now I'm going to do 3 subtract a negative 2. Now, positive 3. Pulling this out. Do I have a negative 2 to remove? Again, I've got to create 0 pairs. So I'm going to create the 0 pair so I can have a negative 2. If I remove the negative 2, can I do that? Can now. And what do I have?
Positive 5.
Positive 5. Now, let's do the last one. This is the one where I'm like, guys, you don't have to do that change at all. Let's talk about that one. I need negative 3. Can I remove negative 2? Absolutely. Gone. What's my answer?
1.
Negative 1. Now, when I go back and I look at this pattern, what do you notice?
1, 5, 5, negative 1. But this side, the answer side, the signs, negative or positive, mirror the first digit.
Oh, that's awesome. Very good. Also, if the signs are the same, what did we do? We just subtracted, right? The signs are the same. I just get a subtract. But if the signs were different, I had to create that 0 pair, which allowed me to do what?
Subtract.
Then I was allowed to subtract, and creating that 0 pair allowed me to subtract, which goes into saying that I changed the sign of the second number with the addition, right? So they start to see that pattern. But if I got negative 2 and I'm going to subtract a positive 2, I have to create a 0 pair. There has to be a 0 pair there for me to do that. And so therefore I need to change that sign. It gets into that, but we never tell our kids that, right? And so this allows them to start building that understanding of what that looks like on a number line. Because if I'm at negative 3 and I want to subtract a positive 2, technically, what am I doing? I'm adding another negative 2. So it gets into that for them to start to understand. And so I love this for that purpose, for getting those addition and subtractions and them understanding what 0 pairs look like, how they can use those, what's happening on the number line. All of those things are, and we don't have enough time. I could take up this entire hour just talking about these beads and how we can do integers, but unfortunately Cricket needs some time too to do some other things. But if you want more information about this, I can definitely help you out. Katie, you were going to say something.
Oh, I was just saying that this is making the nerd inside of me so happy. It's reminding me how much I enjoyed math class.
Well, and
Oh,
our big, I don't know what to call it, our big message here is that math can be understandable for all your students. You can make it so that it is understandable to each and every kid. They have to make sense of it for themselves. You can't take it out of your brain and plant it in their brains. It doesn't work that way. But you can give them opportunities to work with materials and other things that will help them make it make sense to them. And I know this, if you've not seen bead string work, or if you've not taught it integers on a number line before, this may be like, what'd she do? What the hell, how does that work? And I hate that you don't have your hands on it, because if we were doing this in person with stuff, it would make a whole lot more sense. So when you do it in person with your kids, with stuff, with things, manipulatives, it just makes so much more sense to them.
Yeah.
And Cricket, that was one of the things that I think we wanted to have this professional development for, was for different ideas that our teachers could see when they go back and watch this, because it's really hard for them to, watch during the day because they're in class. But we wanted to give them some ideas of ways to make math fun, and to see there's little things that you can do that can make something so much easier for me. I mean, I years ago, I remember them putting, up on the board and doing the positives and negatives, and it just always depended upon the teacher and how the methods that they used made it so easy to understand, or made something a little harder to understand. And that was our hope by having a math like this for our teachers.
Sure.
Thank you.
I hope that it helps with that. And there's a lot more where this came from, guys. There's all kinds of stuff out there. This is a tiny little tidbit. Stephanie, did you want to say more?
Yes, usually when I start this, I start with the teachers actually building the zero pairs, just like I would do with my students. And then we move into addition and subtraction, and I teach those together. And the reason I teach those together is so that our kids can actually see what's happening each time and do the comparison. And I leave that pattern up with those numbers so that the kids can make comparisons, and they need that option to have that. And then the other thing that I do is, like I said, we do it on a number line, but we also do it with two-sided counters. We use those. There's a lot of options that you have, but it builds for our kids just doing those movements many times and being able to see it. But the other thing that I use is the algebra tiles, which Cricket's going to go into. Cricket, do you need me to model those or not?
If my dock camera works, I'll be fine. We'll see.
Okay, then
Thank
I'm
you.
going to give the share back over to you.
Okay, thanks. And as Stephanie said, we'll do the same kind of thing with algebra tiles. And if you're sitting there wondering, what does she mean zero pairs? It simply is that one positive and one negative added together equals zero. And as long as I'm only adding zero, I can make a problem simpler by adding all those things to do. For instance, when she didn't have two negative beads to remove, she could add two negative beads as long as she added two positive beads to equal the zero pairs. I hope everybody was following that. Some people came in the middle too, so sorry, they're your patterns, Stephanie. We could have gone on. And again, leaving that up there and having them draw their own conclusions, as opposed to say, if the larger number is negative, your answer is going to be negative, or if the larger number is positive, or two negatives make a positive when we get to multiplication. All those rules roll around in kids' heads and get confused, and they try to apply rules to things that don't make sense. And it's just, understanding it is so much better than trying to remember what you've been told.
I'm
Building
so
that.
glad you said that, Cricket, because what happens with the beads or the tiles or the foam block, whatever you use, all of a sudden they start seeing it in their head. As soon as they see the number, they see those objects in their head, making those zero pairs or removing or adding, and all of a sudden it's a visual, it's a concrete visual that they're able to see, rather than, I don't know about you, but that's how I was taught. positive and a negative, take the side of the highest, all of those rules. And like Cricket said, they just get all jumbled around and make it very difficult.
Yeah, and easy to forget. If you're just trying to remember a rule, it's easy to forget a rule. We're going to do that, all this again with the algebra tiles in just a second, but I wanted to emphasize, we have walked the line, how important the number line model is for students from kindergarten through 12th grade. And we can use a double number line in middle school to look at ratio and proportion. We can show you a lot of things with that. But number lines are a huge, important model for kids. So please be using number lines no matter what you're teaching. And one way, and I know Stephanie's done this, is to put one on the floor and have kids literally walk the line, build a number line on your floor, or go out and draw one with chalk or paint on the asphalt outside, and have kids start in one place and then give them an operation and have them walk the number line to get to the answer. That physical, and we talk about manipulatives a lot being concrete and visceral for kids, but also movement is a good thing to use with students to get them thinking through what they're actually doing when they compute these things. I threw this organizer in here just so you'd have it. We talked a lot about algebraic thinking. This is a way to have kids record. They can draw a picture of the model. They can do a numerical recording, a table or a chart. They can write it in algebraic terms. They can do a graph. They can write it in words. So this is just a way of, I wouldn't do this all the time with everything, but it's a good way to get kids, when you're introducing especially algebra with kids, functions particularly, this is a good way to get them to see that all these are different ways of saying the same things. And back a little bit to the idea that, well, let me go on with I wanted to throw a quick thing in here about the equal sign, because it's hanging up a lot of your kids in some ways. The equal sign literally is taught. It's in the standards, the KAS, at first grade. So kids have been talking about the equal sign from first grade on. Unfortunately, what a lot of them think it means is, and the answer is. Which is not helpful, because that's not what it means. So they look at a problem like this, and what do a huge percentage of kids, even middle school and high school kids, put in the box? What do you think they put? You can unmute, guys. It's okay. The number one answer for this problem, my wait time isn't as good as yours, Stephanie. The number one answer for this problem that they write in there is 12, because they think 8 plus 4 equals, and then you write 12. They need to get the idea that the equal sign is not operational, it's relational, and that what's on one side of the equal sign has to balance what's on the other side of the equal sign. This is true and this is an algebra problem at a very early level. That's a variable. That's what could it be in the middle, a blank box. But this is what leads to a lot of problems later when they get to high school algebra and they're doing the same kinds of things. They're not thinking about balance on either side of the. So what number should replace it if it's like that? 12. Incomplete understanding, they think equal sign means and the answer is. And we usually do this problems all this way. The problem, the expression first, or the equation, and then the answer follows, instead of flipping them sometimes and writing them in other manners. Again, the equal sign is relational, not operational. Equality is a relationship, a balance between two things. And then less than and greater than, the inequality tips the balance one way or the other. Please don't teach your kids alligator mouth. That just goes all through me. I threw this in as another thing you can try. You'll have this slide deck. So this is an interesting problem, just to get kids using some deductive thinking, some algebraic thinking, to determine how many seals would have to be where the question mark is in order to balance with the polar bear, to balance out the zebras on the left. And we're not going to do this now because it would take us our whole time to work through it, but it's there for you to play with. If you get stuck and you want to talk about it, you got my email address, holla. Here's another way you could talk about the balance in an algebraic problem. algebraic equation is with mobiles, and there are websites galore with these. So if each heart equals 2 and those are balanced, the 3 hearts and the trapezoid and the heart, what must the trapezoid equal? I am going to wait you out on this one because you all should be able to get that. Go for it. What's the value of the trapezoid, the orange trapezoid?
2 hearts.
2 hearts. So what would that be? What number? 4. Does that make sense? Somebody may have thought of it differently than you did and gotten the same answer or not, but it's a way of thinking about balance. Here's a little bit more difficult one. But you can figure this one out. I'm not going to take a whole lot of time to do that. Anybody want to have, just don't tell me an answer for the values of the different shapes, but what's something you notice about it that might help you start solving this problem? I don't want an answer. I just want, what are you thinking to start with?
Each side should be 30.
You got 2 sides there and they have to balance, right? So 30 and 30, what else? Do you notice?
The left side with 2 prongs is balancing.
So that has to be balanced. And if the whole thing is 30 on that side, what does each of those have to be?
15.
So could we work our way through this logically and figure out some values there? Notice we have triangles on both sides. We have some rhombuses on both sides, rhombi on both sides, or squares tipped up. We could figure this out. We could work through that and go through. I'm telling you, there are thousands of these out there. I would start with very simple ones with your kids and work up to the more complex. Another thing.
I'm sorry, Cricket, but just encouraging them to have that conversation and talk about it, that's the math, is having them just to be able to talk about it and not fearful to express their ideas for fear it's going to be wrong. Because as Cricket said, they may see it differently. You may arrive at the same answer, but get there differently. But those kinds of activities really encourage that conversation.
And those conversations inspire more thinking because somebody's thought may get you going on your thought, get it? And I wouldn't give them hints. I would just let them in small groups talk to each other, even in pairs, and see what they can come up with. And then compare answers with each other and see how they're thinking. Let them talk to each other a lot. Another method that's really good when you're doing this early introduction is, this is a very dated picture, obviously, look at the prices, but put real, go to McDonald's and find prices and put them on here, and let kids build different collections. If I order this, this, and this, how much will it cost to start with? Get them building up, and then say, we went and we spent $32.55. What could we have bought? What different combinations will add up to that? Or we bought 3 cheeseburgers and 2 other items, and our total, I mean, you can make hundreds of problems off something like a menu board.
And you
Or
can also go out, excuse me, Cricket, and go to restaurants and get their carryout menus and provide the different choices for the students. And it is providing them with entry points all over the board for the mathematics.
yeah, for everybody to be involved, yeah. And things that appeal to kids. I mean, talk fast foods and teenagers here, yeah. Or whatever you think would appeal to them, get some prices and do it. Here's a different take on the same kind of thing. Going to the fair. If the cost is $3 per person and each ride costs $1.25, if all the friends rode all the rides together and spent a total of $42.75, how many rides did each person ride? And you have to notice at the very beginning of this problem, the word 3 is spelled out. It's not a number. So kids who go in and grab number pluckers, who go in and grab numbers out of word story problems, are going to miss that. They need to think about how many kids were there. And then you can back up, go to, backwards mapping, go get from the total back to how many rides each person did. That's a multi-step, multi-operational problem, which is appropriate for middle school kids. They should be able to do that. And I don't know if you've noticed on the KAS, but the KSA, sorry. If you haven't gone in and looked at the released items lately, you need to. They're not just computations with multiple choice answers. There's a lot of multi-step. There's a lot of having to explain. There are a lot of things in there that are better questions than we used to get that require more thinking on the kids' parts, which is a good thing. Because our bottom line in anything we do is not getting right answers. That's important, but it's not the bottom line. The bottom line is mathematical thinking. We want our kids to be mathematical thinkers. We have technology at our fingertips that can compute. We don't need to have human computers necessarily anymore, but humans need to input the data and humans need to know if it's a reasonable answer. So they've got to be able to do it. They just don't have to waste time doing it when they can have a machine doing it. Anyway, another way to go with this is begin with a problem like 2 times 5 plus 5 equals 3 times 5. Is this a true statement? And then will it always work? Could I plug any number in there besides 5 and would this still be a true statement? A way of getting kids to generalize and make sense of relationships. And again, back to opposite sides of the equal sign. So you ready? More math. Woohoo. We talked about CSA last time. That's concrete. C stands for concrete. The S stands for semi-concrete. The A stands for abstract. So with concrete, you're actually building it with pieces you can pick up and chew on, as I used to say. With semi-concrete, it's a picture of those pieces. And Kelly referred a little while ago to getting the picture in your head. This is exactly why. I mean, we're going to do something with algebra tiles here, but your kids aren't going to walk around with a bag of algebra tiles in their pocket all the time. None of us does. What they have is the picture in their mind of those pieces, and that's there forever. I have watched more kids in the middle of state testing draw pictures on their scratch paper to solve problems. Yes, they've got the idea in their heads. They have the conceptual understanding and they know how to use it to solve problems. That's what we're after here. So semi-concrete is a picture of the concrete at first, and it may end up just being lines and dots or other things, but you start out literally drawing a picture of the concrete, and then we work our way to the abstract. So here's 3 different ways of showing 2x minus 5. With pieces, manipulatives, with pictures, with numerals. Here's another thing. We'll get to some of this in just a minute, but you'll notice at the bottom, there's a picture of the manipulatives. There's a drawing of that in the top right, and then there are all kinds of abstract expressions of it with numbers and symbols. Okay. And back to Christina Tondevald and Karen Karp's idea. We used to talk about doing it almost linearly. Do the concrete, then put the manipulatives away and do the pictures, draw pictures, and then put that away and make kids do it with just numbers and symbols. And we're so far from that now. They need to see all 3 at once. Sometimes they're doing the manipulatives and you're up recording what they're doing with pictures and with numbers. That's fine. Eventually the kids need to be doing all 3, because what we found was when we just did one and then put it away and did the other, they didn't make any connections. 2 weeks later, you're doing it with abstract numbers. They're not thinking about the concrete manipulatives that would help it make sense to them. If they see it all at once and connect it, makes a whole lot more sense. The big idea here, concrete and visual representations are extremely important in developing conceptual understanding. Have we said that enough times now? One more time? Okay. Math is my favorite. Here we go. So here's some ideas about algebra tiles. Let me see what I've got. Okay. Yeah, let me back up. I'm going to just hopefully toggle to the, wait a minute, let me turn it on. Be like you, Stephanie, this better work. I'd be upset if it doesn't. Okay. Did it do? No, come on.
Pin your screen, unshare and then pin your screen.
In my screen.
Yeah,
There
pin
you
your,
go.
here, I might be able to pin your screen. Let me see. There you go.
I think I got it. Okay. So here are some algebra tiles. Here are the three basic algebra tiles that you get when it's going to be backwards to you, isn't it? Okay. Do it this way. All right. This is a unit. A unit is a unit is a unit. It's also, well, two-sided. So the yellow side is positive, the red side is negative. This is the length of this side of it is the same. This green piece, the end of it is the same length as a unit. So it's if this is 1, then this side of this is 1. But this side, we don't know. And the kids will put all these over there and try to say, oh, it's 5 of them, but it's not. It's specifically manufactured so that it won't equal however many of these. So this side becomes X. Does that make sense? It too has a negative side, could be negative X. So I have, let me do this. Here's 1. Here's negative 1. Here's X. Here's negative X. And the length of this square here is the same. So this length is X. So the length of the side of the square is also X, as is the length of the other side of the square. So this side is X, that side is X. What I have here is, am I still upside down? I'm sorry. Where's my flip thing here? Okay, sorry. Looking at it backwards. This whole thing is X squared. And this then would be negative X squared. Does that make sense to everybody? You have units, you have X's, and you have X squareds. So we can start out doing some of the same things Stephanie did. If I wanted to just work with units, I could get a bunch of units on here and talk about the same problem she just did. We could do 3 plus 2, negative 3. If I had negative 3 plus 2, positive 2, I can put those together. Where are my 0 pairs up here? Well, these two would make a 0 pair because together they equal 0, right? So I can remove them. These would make a 0 pair because together they make 0. I'm left with negative 1. So I started with negative 3 plus 2, and I'm left with negative 1. Same thing we just did, but with these pieces instead of the beads. Everything transfers totally. We could do the same thing with the x's. What if I had 2x minus 3x? Or let's say 3x minus 2x. If I have, no, 3x minus 2x. If I have 3x, 2x plus a negative 3x, I again can match. So this is 2x plus a negative 3x or minus 3x. I can put my matching pairs together and I'm left with negative x. Same thing with the x squareds. So with kids, I would spend some time for sure going through I wouldn't start with all three. I would start with just the x's and units and build all 4 operations with them first before I got to the x squareds. And I'll throw this in here just to confuse the issue. If you teach algebra 2 or higher and you can use, if you have these algebra tiles, which is the old, how they've been for years, you can do algebra 2 things. You can add another variable by making this y squared, this an xy, and this x squared. But you can also buy add-on kits that look like this. So if this is my x's, these are my y's. They are not the same length as the x, obviously. So this is y, this is a negative y. Same units, units are units are units. This is y squared, obviously, right? Same on both sides, it's y on both sides. So y, negative y squared, negative y squared. And then this one just happens to be an x by y. So this is xy and this is xy squared. So you can go on with this into much higher level algebraic thinking with these additional pieces. But for today, we're going to talk a little bit about, I want to get to, we've got 12 minutes left. Here I am again. How do we use this for multiplication? I think you can get the addition and subtraction. And Stephanie, you were gonna, I have this little book. I couldn't find my Didax books. Guys, there are all kinds of little skinny, quick algebra tile helper books that are very cheap that you could get if you want a tutorial on all this, or you can go online and find things. It's not as complicated as it may look just seeing it for 5 minutes here. So what if we wanted to do, I'm gonna do my famous here. When they're little and we want them to multiply 2 times 3, let me get to this with these. They may have done this before they get to you. They may be looking at 2 times 3 and we have them do 2 groups of 3 with base 10 pieces. And then we mush them together and we have a 2 by 3 and the total area is 6. So how do we take that and make it a 12 by 3? We need a rectangle whose dimensions are 12 by 3. Multiply 12 times 3. This would be a 12 by 3, right? So the length of this side is 10, 11, 12. The length of this side is 1, 2, 3. So this is a 12 by 3. The total area is 10, 20, 30, 6. You see it? Can't see very many faces. So what if I wanted to make this 12 by 13? Then I've already got 12 on this side, right? I need to make the horizontal side equal to 13. One way I can do that is like this. This side is 12. This side is 10, 11, 12, 13. So now I have a 12 by 13. What's the total area? 100, 10, 20, 30, 40, 50, 6. If I wanted to do decimals, what if this was 1 3/10 and this is 1 2/10? This now is 1 whole, not 100. These are tenths, these are hundredths. It's the same picture. It's the exact same thing. Now the length of this side is 1 3/10. The length of this side is 1 2/10. Total area
0.6.
is 1 whole and 56 hundredths, right? You see it? Too fast, I know. What if I wanted to do fractions? What if I wanted to do 1/2 by 1/3? All of this is the area model for multiplication, which your kids really need to be exposed to. If they can do that, I show you real fast with algebra tiles too. So if I want to do 1/2 by 1/3, I would need a whole. And then the length of one side of my rectangle has to be a half, and the length of the other side has to be a third. So here's a half, right? And here's roughly a third. So I could either color in overlapping or where's my rectangle whose dimensions are 1/2 by 1/3? It's right here. And what part of the whole is that? 1/6. So now we're down to what if I wanted in algebra to do x plus 2 times x plus 3? Then I'm going to do that with my algebra tiles.
If you have a student who's having trouble like keeping those tiles organized and they need something to put it on the outside so they can see it, You can use wiki sticks, and that helps a lot. There's also graphic organizers you can use for multiplication.
Yeah, and there's just a mat, a piece of paper with it has a thing on it that looks like this. And then, so this side needs to be, what did I say, x plus 2? So the length of this is x, 1, 2. The length of this is x, 1, 2, 3. Then I have to fill in my rectangle. Don't pick up with units.
And so by using those, I always talk to the kids about making sure that they know that that's a positive 2. And let's say it's subtract 3 at the bottom, that would be a negative 3.
Right. And you would use negative pieces down here, but the red side. So this side is x plus 3. What's the total area of my rectangle? So x plus 2 times x plus 3 equals what? What do I have? X squared, 1x, 2x, 3x, 4x, 5x.
And this allows them to see those like terms a whole lot better
Yeah,
than just adding those at the bottom, because we
Yeah.
have that so often.
because literally they're the same piece. And you know, when you talk about combining like terms, they're picking up the same piece. They get that. Does that make sense? Have you all used algebra tiles at all? I mean, this is pretty basic, just doing this. The converse is also true. If you want to factor polynomials, you take out the whole multiplication, you know, both sides of the rectangle. You're trying to find the area. Division, you know the area and one side of the rectangle. You're trying to find the other side. So if we took, what if we were wanted to do, what have I got? X plus 2. Let me do this. X squared plus 6x plus 8. So I've got x squared. I've got my, okay. I've almost got this out there.
I love it
Here-
when kids find out the number is prime on that, and they know it has to be one in the other number.
Yeah.
That's my
Yeah.
favorite.
And they pick up, they understand that because they're seeing it, right? And doing it. So here's my total area. I've got my total area out there. I have to make a rectangle. And I'm usually gonna, after a few of these, you start doing this and just playing with it. So I want to factor that. I know that one side of it has to be, well, let's just factor this. X squared plus 6x plus 8. I have to make a rectangle. So I just keep playing around with it for a minute. And they get better after they've done a few, they start seeing things. So if I put this one up here and then try to fit my units in, it's not going to work, is it? I might start there.
What a lot of my kids realize after the first 2 is that they have to get their units correct before
Yeah.
they start playing with the X's.
So I move the X's around and now, do I have my total area? X squared, 6x plus 8. Oops. What's the length of this side then? It's x plus 2. What's the length of this side? X plus 4. So if I factor this, I'm going to get x plus 2 times x plus 4. You can take this to all kinds of levels. You can do completing the square. I mean, algebra tiles are a basic tool for making algebraic thinking visible to kids. I don't know how else to say it. I don't know how anybody teaches algebra without them. If they've come through using an area model, life is a lot easier. If not, you just stop and do that with them. It's perfectly doable. And I am going to stop sharing, I think.
Cricket, before you stop sharing with those algebra tiles, will you just do a simple one like 2x plus 4 equals
Yeah.
12? I mean,
Okay. So 2x.
yes.
Let me erase some of this again so you
Yeah,
can
I'm
see.
trying to say erase some of that because I
Yeah,
think
it's
it's important that they see how to do an equation too. And there are, again, there's maths out there for them to do this, but really the only thing they have to do is draw a line.
limit.
This is what we learned as FOIL, right?
We learned as FOIL multiplying two binomials, but
Yeah.
FOIL only works for binomials for one thing. And it doesn't work for other polynomials. And kids get so confused about what it means and how to remember it. And I hate FOIL these days. Okay. So if I had
It doesn't exist.
2x plus 4 equals, what'd you say, 6?
Yeah, that's fine.
Yeah. So I've got my two x's. I've got my 4.
Write that above it so that they can see how the steps work too, because I try to do that often. So write 2x plus 4 equals 6, and we'll work it out as we do it.
Okay. Go ahead, Stephanie. Talk it through.
Okay, so if I've got 2x plus 4 equals 6, the first thing I need to do is I need to get my units together. So what do I have to do? Now, I have my kids create 0 pairs, but they get to the point where they can just flip them, right? And
Right.
so they will take the 4 from over here. And do you want to create the 0 pairs, or do you want to do that?
I'm trying to get enough units out here to do that. Yeah.
Sorry, I
If
get excited about this.
if we wanted to create 0 pairs, we'd have to how many would we need here to zero these out? We'd need 4, right? And if we do 4 here, we have to do
Or on the other side, because they have to equal, right?
equal. Right. So if I do that and bring my 4 and my 4, does everybody see those? Then these will 0 pair out.
Yep.
And
And on
these
the other side, you will 0 pair out 4.
4. And
And
then I
then
have 2x equals 2. And I can kind of just go like this. X is going to equal whatever half of this is, right?
Well, when
See
I
it.
0 pair those out, I go ahead and I say, okay, I'm subtracting 4 up here, and I'm also subtracting 4 on the other side. So we've done that part. Now what have I got left? And so they'll see that 2x equals 2. And now I say, what does the 1x equal? And we're going to
Right.
fair share. They've heard fair share for their whole lives, ever since kindergarten. And we're going to divide. So if I divide the x by 2 and I divide the 2 by 2, I'm left with 1. And so simple equations, they can do very easy with algebra tiles. Actually, they can do very complex equations with algebra tiles, and it's okay.
Yeah. They can do pretty much anything with algebra tiles, and it will make sense to them. Okay, we're running out of time. Let me get out of here.
Sorry. I just had to throw that in though.
Oh no, yes, I understand.
Well,
believe me.
this is just to give you a taste of what it is. Not expecting you to totally understand and be able to implement
After
classroom
after
from
this
this.
little bit, no.
So
was-
if it piques your interest, reach out and we can do some further training.
And would be happy to. We all love doing this, can you tell?
It just makes me want to take a test.
Well, you would be able to do even better. So let me get down to, this runs through all those. Here's a picture of what we did. Just some extra things. Here are some resources we think might be useful to you. I put this in, if you get a chance, Howie Hua is phenomenal. And we did some patterning last time, and he goes through some thinking pattern. He has multiple TikToks out there and YouTube videos. He's a great resource for you too. This is some more patterns. We did some visual patterns last time. This is algebraic thinking with pieces. And what else can we do, guys? What other math resources? How else can we help you? Here's our contact information one more time. Oh, sorry. These are more resources. These are virtual manipulative resources, particularly.
Also,
And then-
I threw a bunch of resources, Cricket, into and I know we're going over, into the chat. So if you guys can grab those out of there throughout the time, or if we can print the chat, we'll do that.
Okay. So what questions do you have at this point? Let's get back to just, and you have access to all this, so don't panic about copying anything down.
I'll post it with the video links and all that good stuff.
Thank you. Other thoughts, other questions? Are you thinking there is something you can take and do from here, and I don't expect you to go back and do algebra tiles tomorrow. That's not what anybody's saying. But we sure would be happy to come help you do that. It's not something you just can do after 5 minutes for sure. But with a little practice, it's not that hard either, guys. You'll pick it up. It's doable for you and doable for your students. Anybody? Go ahead.
Pretty sure Dr. Nolan has a set in his office that he does every day. I'm not 100% sure, but no, just thanks for the information. It's good, very concrete, hands-on for kids to put it together. So appreciate you spending the time to do it.
We're happy to. It's what we do. And we're nerds enough that we love doing it. So we'd be having my
Outstanding.
standing offer. I won't speak for everybody, but my standing offer is I don't come demo teach much. I don't see that being, I will, but anyway, I love to come. If you want to try manipulative, if you're in my area, I'll come team teach it with you the first time you try it. So that when you'll have an extra pair of hands in the room and a little backup if you're shaky on it. I think if you just jump in and try, that's how we learned. We went in and just winged it to get going. Once you see the ahas in kids' eyes when things make sense to them and they can explain it, they can argue with each other about it, and all that, that's what's worth it. That's what's important here. So
Absolutely. Thank you.
sure. Thank you all. Appreciate you taking the.
Yeah.
Go ahead.
Thank you all so much. I just wanted to just take a second as we wrap up to thank you so much for all of your time and for investing in state agency children. These are, as you all know, kids who have some pretty significant learning gaps when they come into the state system, and we're working really hard to close those gaps for our kids. And resources like this help us to be able to do that in a much better way. So we appreciate all of the support that you've provided so far and that you're going to continue to provide through your co-ops as we continue to partner together. So thank you so much. We appreciate you very much. And our teachers out there in the field will certainly be in touch as we post this and connect you virtually back with many of our teachers across the Commonwealth. So thank you all so much. We appreciate you.
Thank you for having us, and we're serious, and there are more of us. This is just half of us, so we're out there if you need us, when you need us. Thanks. I'm going to stop the recording, so if anybody, maybe.